formation of compiler writing from a deep black art, as it was probably 30 years ago, to a relatively straightforward matter, which anyone will do if you pay them the price. We then, of course, got the change in the mode of use of hardware, because, you know, back in 1962, we had printed reports and we had cards going in, and we had files going in and we had files coming out, and we had some data on disk, which was referred to and modified. Now, of course, we have an enormous jumble of different ways of using hardware. You know, we've got the person at the workstation with the mouse, very important, the mouse. We've got networks, we've got, and I've got a nice collection of slides here in the sheet music on that if we want them. But to move on, we've also had the things that remain true. You know, there are things. I went on my first programming course at Christmas 1956. Indeed, I think Christmas Day that year fell on something like a Thursday. Therefore I started my first fortnight's programming course on something like Monday the 29th of December. In those days there was no thought of having New Year's Day as a holiday. I mean, you really worked then. And of course there are things that were true when I went back and implemented the kind of first commercial systems in 1957 that are still true now. And other things that have changed totally out of recognition. But one of the things that's always been true, notwithstanding our 96-bit workstation, is that the vision is always miles ahead of the technology of the time. In computing, it's jolly easy to have ideas. You know, you can line your path and you can think how things are going to run, and you can say, I have software that does this, and then you try it out, and you know, it goes like swimming through porridge, you then get bogged down in matters of optimization, and if only I had, used to be, if only I had some more memory, you know, if I could have 512 words instead of 256, everything would be solved. Now, of course, with all the windows, if only I could have a 24-inch screen and 2 mice instead of a 19-inch one. So you've always been bumping up against the technology. And you know, if only we could have another couple of hundred MIPS so we didn't have to bother about optimizing things. We could just get on and do things, not worry about performance. So that's true. And then the other thing that's always true is that even when the technology catches up, it's, well, I've got a visual here that says 10 to 20 years from profits to profits, but it's of that kind of order of magnitude from most things when you start doing the work before you actually have a product that is used and makes money. This is true of paging systems, 57 to about 79, 80 when they really came to pass. High-level programming languages, what we now call third-generation programming languages, trying to write compilers 59, 60. I can remember conferences in the early 70s where IBM people would say, should you use COBOL or assembler to really get productivity? And relational databases were more of that anon. So let me now talk about the 1960s. And I'll skate over the 1960s because with Bill here, we have an excellent description of the 1960s in the first chapter of his little green book. He can therefore, there's several varied descriptions. There's not only Bill's, there's several others, but he can, as it were, correct me insofar as I'm going wrong. The 1960s, now, when you approach history, and when I was thinking about this lecture, I suddenly understood, you know, why Trevelyan wrote Social History of England, because, of course, you can approach history from the point of view of battles and events and dates and people, and that's tremendous fun to a point. But then you can also approach it on the basis of what was really happening under the covers. And you've got exactly the same when you get down to the history of any computing topic. You've kind of got the committee meetings and the votes and the people and the project starting up and the reports being produced, and that's the kind of the battle view. But then you can also say, what were the underlying ideas? So first, we'll take it on the basis of dates and battles. Well, let's think of the battles, or think of the different things that happened. There's from Bachmann's IDS to the Codicil DBTG report. 1962, or thereabouts, Charles Bachmann and Susan Brewer produced something called IDS, called the Integrated Data Store. And they did that because what they wanted was interrelated files held on disk, because they had requirements for that in applications connected with manufacturing. And they did that because they got the need for it. There was something called APL, Associative Programming Language, which was based on PL1, produced independently by Dodd. That did the same kind of thing. And I suppose it was that led to the formation of the Codicil List Processing Task Force, which existed for 2 years, and that had a simple idea. You know, one of the strange things about computing, I remember a few years ago, some students said to me, why do we learn Snowball as a programming language? Why can't we have a modern programming language like Lisp? Because they didn't believe me when I said that Lisp predated Fortran more or less and came back. And of course, there were lots of papers in ComACM and Computer Journal and things in the round about 1960 talking about Lisp processing. You all understand Lisp processing. You essentially regard your memory as a collection of cells, and you link them together with pointers. And you have pointer chains, and you follow these things around. And what was really said here is, well, wouldn't it be useful in data processing if we used the same kind of linking techniques, not between cells in memory, but between records held on disk? So let's have a task force to look at it and see whether this can be done usefully. So that's why it was called the List Processing Task Force, and it was the Codicil List Processing Task Force. COBOL List Processing.
Yes. It seems an extension to COBOL.
Ah, right, yes. But why I'm saying it's the Codicil List Processing Task Force, because I was about to say that Codicil was the body at that point responsible for developing COBOL.
Who was the task force on the COBOL language?
Yeah. 1967, it turns itself into the database task group, but it's essentially the same theme of work. Bill will know more about this than I, but as I understand it, they felt that Lisp processing had overtones of beards and sandals, and that it was necessary, as it were, to, those are the days, you know, if you worked for IBM, you had to wear a white shirt and a tie, and you took your coat off in the presence of the customer, or jacking it off in the presence of the customer. So therefore, it was felt that a database task group had that image. You know, you wore a white shirt and a tie, and you never took your jacket off in the presence of the customer. And it then produced its really quite famous Codicil database task group report, which came out in July '71. So that was one theme. That's one of the early themes which went through. Then there was another theme, which I call from Guam and RATS to IMS. Guam was generalized update and access method. And roughly speaking, no, exactly speaking, what Guam was, it said, well, we all understand COBOL records, and COBOL records only allow you a repeating group at the end of the record. That's pretty limiting. Why can't we have COBOL records, which can be very large, with unrestricted repeating groups within repeating groups, hold them on disk, and let's be able to look at bits and pieces of them, subsets of them. So that was apparently a requirement to, in relation to managing the data connected with the Apollo moon landing project. RAT's remote access terminal system was, of course, what would now be very familiar, getting access to data via terminals. Those were put together at some point around 67, 68. And in 1968, it was frozen for the launch of the moon rocket. You know, even then it was realised you couldn't have people changing the software while you're in the middle of launching a moon rocket. So it was frozen. And then in 1969, IBM released this as a product. And this is the one exception to the rule that it's 15, it's 10 to 20 years from profits to profits, although whether IBM actually made any profit out of the early versions of IBM IMS, I know not. However, it was released as a product, and that was one thing, and has been improved ever since, and is still in existence to this day. Indeed, 2 years ago, or is it 3 years ago, we had data down at Hersley from the large IBM mainframe users, which showed that in terms of volumes of data, 50% of the data was held in vSAN, the ordinary file access method, didn't use database management software at all. 30% was managed using IMS. About 12% was managed using the IBM relational products, DB2 or SQLS, and the other 8% was all
an evolution it evolved into. I think it's fair to say that there was caution about going otherwise at the early days, and it was the great benefit of accrued, of course, of starting early, that a progressive stepwise advance could be made into the ultimate development, which became very extensive indeed. So I think I will turn to view one, which is in fact the start. It starts the selection of themes, and it is in fact shows both the foresight and the caution which were taken by, if I can get it right, and can we turn down? I think you'll all recall the legendary A.J. Young, who opened the ball, as it were, with his address to the production engineers in 1955, with a program there which I would extend either way. In fact, it's quite good to have got it a bit on the large side, because you can see that it covers a considerable spread of these dimensions. A program for the development of automatic process control system design, which was his rejoinder on being asked to join the automatic factory meeting, this automatic factory meeting in 1955. And he restrained himself in that instance to say a list of prerequisites, as opposed to a number of other authorities who were, as you were, raring to go. And from this you can see that he had worked up from origins. I'll try and get this across reasonably well. The origins were the characteristic components of his system, the development of control equipment. All this, to get this correct, was prerequisite to the development of systems design. This this section here, you'll see, will be very readily recognized by those letters, and at the base we have a telling reference that there will be company was, and I'm just reminiscing from a press article, a lay press article in the business press about 1956, when it was pointed out that ICI had already acquired 5 different installations of variously business mainframe computers, ranging from the numbers I think were 2 Elliots, 402 and 405. There was I think the first Pegasus was in by then. There had been a Hec4 area of process instrumentation, and this was elucidated in AJ's textbook, An Introduction to Process Control System Design, 1955, which was, I would think, represented the advanced state of art of the classical process control system, dealing very much with the characteristics of plant and process operations. But in introducing that and in laying out the program for the laboratory, he emphasized that the one area which was, if not deficient, was at least very elementary, was the characterization of chemical processes. And it was this, the pursuit of this theme, which led to the makeup and the balance of skills, background of knowledge, the body of knowledge, in fact, which AJ recognized was necessary to produce a complete, a team or a force, and it was on this first arm, equally important, was to provide a considerable stimulus for the development of general purpose computing, if I put it that way. But I would really say of computing, we can use the phrase of mainframe computing in those days, large, the most powerful computing that could be conceived as a general service to technical development. And it was this was characterized historically by the establishment of the mainstream of process control and process development as a system which required computing, and how this was supported by computing which had itself to be part of a system. And I need not dwell very long on it, but that, of course, was an essential that had been grasped and expounded by AJ and by the team, that this was the line of development was essentially that of systems, and you could define systems as you like, perhaps through computing. And this was, at the time, it was recognized as early, and in retrospect one can see that it was very early. The notion that the words of those days, I think, the three, before the white hot words, but the words of those days were automation, communication, and electronics. That's rather suffused with the difficulty of doing the task. In particular, of course, one must recall that the standards of reliability of mainframe computing in those days, indeed of any electronics, process electronics, was not adequate for the operation of a process in real time. So that the inhibitions about safety and practicability were quite severe. But again, the background of physical science and engineering and computer science and engineering, and the strong liaison which the company science had then and still has with the research. The part of the combination of reliability was to introduce some special logics. Pigalis was not content with diode core logic, it was going to be transistor core logic. And he was right, because the variability of the solid state devices then was such that the addition of that sort of feedback, stabilization, was quite essential. It all took a long time. It was all very hard work. It was all very difficult to keep up to some sort of pace. And in a sense, it was overtaken. But the background that was achieved there was in fact going to help in a next stage of online computing, which was in fact, I can show that here. At the same time as this was being developed, Ferranti had been, among others, but Ferranti, the leading place, had produced real-time computers which were in use for military applications, for guidance computers, were regarded as credible reliability, and with the excellent coordination that AJ has set up with the industry, one of these was made available for trial, and this was in fact put in as the Argus at see what to get. Yes, the Argus application by the then Alpha division to show this how this interaction was working within the plant, within the laboratory and the laboratory's concept for process control and computing systems in ICI as a whole. But in parallel with this, there had, of course, also been the further after the this here. We can see some parallelism in time here. We're roughly going along in time here, beginning from the mid-1960s at the right-hand edge. Over that time, of course, the Ferranti system had been developed and was incorporated as a service, a renowned service, very high repute, and again made it gave great liberation to chemical process investigations. Even if you could not get a complete solution, it was at least credible to attempt sectors of the solution and build up at least a progressive development which was significant in the industrial stage. And that proved to be one of the most expanding features of the lab, and was and was paralleled in divisions. That's the acceptance of computer-based analysis for all the quantitative specifications of process requirements, both continuous, particularly those who've been working jointly in marketing, recognized that this was a real task. And we ran over three sort of principles which had to be here. And one was that people demand simple solutions. Now, the requirement which is there and is not spelled out is, of course, that the only way, in the last resort, the only way to get a simple solution is to start with a valid complete solution and produce a valid simplification. Now, it turned out that with the combination of electronics and graphics and the fact that we had done, I think there's quite a point there, is that the time span on that development was, yes, I suppose about 1956 we started to argue about that. And it took a few months to find, as you imply, Sam, the simple way of doing this. And then some 3 or 4 years to get that, and so it was. But in between that time, in that 3 or 4 years, I was able, and others working in the company and also in the operations research world, were doing some really quite intensive analysis. We were somewhere near at least the requirements for a complete solution of that particular task, for which we could say, well, as you can see, it was trivial sounding, but at least trivial scope examples, yet we could say pretty exactly there where we were cutting corners. The difficulty about the simple, simplistic solution is you adopt it when you don't know which corners you're cutting. One, and I'll quote because one much greater than me has quoted this, is the learning curve. The learning curve and its projection into the adoption of levels of capacity which enable you to learn quickly by essentially making a large number of mistakes. And that has, well, it would require another session to elaborate on the way that particular simplification has greatly misled. I would think, it's less risky in straight science than outside. And it's an obvious need to get the learning stage, but the background is not something